Jai Hind students, welcome to my YouTube channel. Students, I hope you all are in jovial mood and studying very well, isn't it? So before we begin this session, let me tell you something about your mind. Students, you need to train your mind to see the good in everything. Have that positive approach. I repeat, train your mind in such a manner so as to see the good in everything around your vicinity, around your surroundings. Positivity basically is a choice. The happiness of your life, it entirely depends on the quality of your thoughts. And that is the reason why, students, I always keep asking you to always have positive thoughts, to always have positive approach. Clear? So, feel that positivity inside you and spread that positivity around your surroundings. So with that, students, let's begin today's session. Today we are going to discuss the magnetic moment of an atomic dipole, or rather you can say each atom behaves as a magnetic dipole. So we are going to find an expression for the magnetic moment of atom having unpaired electrons, right? So let me introduce this topic with the concept that every substance, every matter is made up of atoms and molecules, and every atom is made up of charged particles, a positively charged nucleus, which is the core at the center of the atom, and surrounded by electrons revolving around it, having both orbital motion as well as spinning motion, isn't it? So basically, the revolution of electron around the nucleus, that constitutes current loop. And hence, whenever there is a case of current loop, there must be magnetic field as per the magnetic fields of current, isn't it? So, the electrons revolving around the positively charged nucleus constitutes current loop, and accordingly, every atom, if it has unpaired electron, then it behaves as an atomic dipole. And if it behaves as an atomic dipole, then we are aware it must have some magnetic moment. So in this session, we will be trying to find an expression for the magnetic moment possessed by an atom due to the revolution of electron around the nucleus. Clear? So that is, atom acts as a magnetic dipole. So we are going to start this topic. So students, let's consider this to be the positively charged nucleus. Obviously you are aware, neutrons and protons, they are the constituent particles of the nucleus, isn't it? Neutrons are electrically neutral, protons are positively charged. So they collectively form nucleons. So this is a nucleus having positive charge. And let us consider this to be a particular orbit of a given radius, right? Suppose its radius is r. This is the orbit of an electron. Electron revolves around the nucleus in circular orbit. Let us consider the electron to be revolving in the anti-clockwise direction, like this. This will be the velocity vector, right? So let us consider the electron, this is the electron, to be revolving in the anti-clockwise direction. Now, since the electron is revolving in the anti-clockwise direction, therefore, the revolution of electron around the nucleus in the anti-clockwise direction will constitute a current-carrying loop in the clockwise direction. So, the direction of the current would be like this, in the clockwise. Have I made myself clear, students? Again I repeat, students, we have considered an electron to be revolving around the positively charged nucleus in the anti-clockwise direction. At any instant, the direction of its motion will be given by drawing a tangent at that particular point. So this is the tangent. This is the tangent and this is the radius. This is the radial vector. This is the radial vector, right? Directed in the radially outward direction. So the angle between R and B is 90 degree. This is 90 degree. And students, if the electron is assumed to be moving in the anti-clockwise direction around the nucleus, then obviously it will constitute a current carrying loop in the clockwise direction. Isn't it? Electron is moving in the anti-clockwise direction, so it will constitute a current in the clockwise direction. Clear? Now, as we are aware, students, a current carrying loop, it does behave as a magnetic dipole. One phase of the loop through which current appears to be flowing in the clockwise direction, that behaves as the south pole, while the other phase of the current carrying loop through which current appears to be flowing in the anti-clockwise direction, that behaves as the north pole. I will again verify this statement with the help of this diagram. This is a current carrying loop. Suppose the current through this phase of the loop seems to be flowing in the clockwise direction. Then this phase of the loop will behave as the south. So magnetic field lines will seem to be entering at this particular phase. While the other phase of the same current carrying loop, the current will appear to be flowing in the anti-clockwise direction. So it will be like this, anti-clockwise. So this phase of the current carrying loop will behave as north pole. We all are aware of it. We have already discussed this, isn't it? So basically, if we consider a current carrying loop, and from my side, the current appears in this loop to be flowing in the clockwise direction, then this phase will act as the south. While the other phase, if the observer is standing over here, from his point of view, the current in the same loop will appear to be flowing in the anti-clockwise direction. So this phase will act as the north. So this one will act as the south, and that phase of the same current carrying loop will behave as the north pole. So current carrying loop, it will have two poles, south and north. So magnetic field lines will enter the south, and then from the north it will make an exit. It will be in the form of continuous closed loops like this. Clear, students? So that can be remembered by using this symbol. Clockwise, that phase will act as south. Anti-clockwise, that phase will act as north. So direction of the magnetic moment is from south to north. We are aware of it. So current carrying loop behaves as a magnetic dipole, and the magnetic moment of a current carrying loop or bar magnet is directed from south to north. So this upper phase of this current carrying loop will behave as the south polarity. This will behave as the south polarity. While the phase which is in the downward direction, that will behave as the north. So this will be south, and downward would behave as the north polarity. So the magnetic moment is directed from south to north. So it will be like this. M stands for the magnetic moment. This is the magnetic moment. Right? So again I repeat, students. What I have stated is every matter is made up of atoms and molecules. Each atom consists central positive core, which is known as nucleus, containing nucleons. The sum total of protons and neutrons are known as nucleons. And the electrons revolve around the nucleus in circular orbit, isn't it? We have considered one such electron to be orbiting in a circular path of radius r. At any instant, the direction of motion of the electron will be given by drawing a tangent at that particular point. So since it is assumed to be moving in the anti-clockwise direction, so at this point, this is the velocity vector, and this is the radial vector, which is in the radially outward direction. Obviously, the angle between radial vector and the tangent at a point is 90 degrees, right? And the revolution of electron in the anti-clockwise direction around the nucleus, it will constitute a current carrying loop in the clockwise direction. And if the current flows in the clockwise direction, then that phase will act as the south. So the upper phase of this loop will act as the south, while the downward phase will act as the north. So the direction of the magnetic moment of this current carrying loop will be from south to north, as indicated by this diagram. Clear? So basically I have tried to draw it a three-dimensional diagram like this. This is actually a three-dimensional diagram. This is the horizontal plane. This is the horizontal plane, suppose. Okay. Now students, we are aware the magnetic moment associated with each current carrying loop, it would be given by IA. For a single revolution, the magnetic moment of a current carrying loop is given by ampere turns into area of the loop under consideration. For a single turn, it would be IA. I is Q by T, and for one complete revolution, it will be capital T. A. So magnetic moment in magnitude, it would be equal to charges that carried by an electron, 1.6 into 10 to the minus 19 coulomb in magnitude. Capital G, it is the time taken by the electron to complete one revolution, which is actually 2 pi r. This is the total circumference of the circular orbit divided by, it is covering the circular path with velocity v, isn't it? So T would be 2 pi r divided by v. So you can substitute this value of T as 2 pi r by v over here, right? So it is 2 pi r into v. Clear? And area of the loop. This circular orbit is considered to be of radius r. Therefore, area of the circular orbit would be pi r square. So the magnetic moment, students, it would be equal to EVR divided by 2. This is a very, very important relationship which we'll be using in the coming topics, right? Put this as equation P. Clear, students? Again I repeat, magnetic moment of a current carrying loop is given by the product of ampere turns and the area of the loop under consideration. So that is what I have written. Current is rate of flow of charge. So during one complete revolution, it is Q by T. T is the time period, which is 2 pi r by v. A is the area of this particular loop, which is pi r square. Substitute all these values and we'll get this relationship. Clear? Now, very, very important aspect is we need to consider Bohr's quantization condition, right? As per Bohr's quantization condition. It states that the angular momentum associated with an electron revolving around the nucleus is given by some integral multiple of h by 2 pi. H is Planck's constant. So mathematically, students, the angular momentum associated with an electron revolving around the nucleus, it is given by, angular momentum is represented by capital letter L. It is given by n times h by 2 pi. N is the principal quantum number, 1, 2, 3 and so on. And h is the Planck's constant. H is the Planck's constant. Its value is 6.62 into 10 to the power minus 34 joule second. This is its value, right? So this is Bohr's quantization condition. Again I repeat, students, the angular momentum associated with an electron revolving around the nucleus is given by some integral multiple of h by 2 pi. N is the integral multiple, 1, 2, 3 and so on, right? So here h is Planck's constant, which is 6.6 into 10 to the minus 34 joule second. So this is as per Bohr quantization condition. Also, students, we are aware in vector form, the angular momentum, you must have done it in +1. It is given by the cross product of the radius vector, position vector and the linear momentum vector, isn't it? So let's see what will be the expression for angular momentum in case of a revolving electron around the nucleus. Now this is r vector. Now momentum, we are aware it's m into v, product of mass and velocity. So obviously linear momentum would be also along the same direction as that of the direction of motion. So let's find out the angle first, r cross p. So the angle is to measure like this, r cross p, right? So let's try to find out the angle. So the direction of the resultant of the cross product of the two vectors is given by thumb rule, right hand thumb rule. So it's like this. The fingers should curl along the direction of the orientation of the angle. Here the angle is to be measured from r to p like this. So the thumb is indicating in the upward direction. So this should be the angular momentum. So angular momentum is perpendicular to both r vector as well as angular momentum is perpendicular to p vector. That is, angular momentum is perpendicular to the plane containing r vector as well as p vector. Here r vector and p vector are in the horizontal plane. So angular momentum is perpendicular to the plane and directed upwards using this rule. Clear? So one thing to be noted is that, students, n vector and l vector both are oppositely directed. So it might be asked in a conceptual question, what's the angle between the angular momentum and the magnetic moment? So the angle between them is 180 degree. The angle between L vector and M vector is 180 degrees. It's pretty evident from this particular diagram, right? Now coming back to this, in magnitude it would be R. Linear momentum is mass into velocity. Here m is the mass of the electron under consideration. What's the angle between these two? R and P, it is 90 degrees. So it will be sine 90. Sine 90 is 1. So L would be equal to mvr. Put this as equation number B. Now students, let's find out the relationship between angular momentum and the magnetic moment. And let us try to represent it in the vector form. Right? So what we do is, from A and B, what we get is M is equal to E by 2, and this is VR. VR may be written as L by M. L by M. So this is in magnitude. This is in magnitude, right? So this is the relationship between the magnetic moment and the angular momentum. Now in the vector notation, because magnetic moment, angular momentum both are vectors, charge and mass, they are scalars. So in vector notation or in vector form, the above expression may be written as m vector is equal to electronic charge, it's negative. So it will be minus E L vector divided by 2m. So students, this is a very, very important result. So what does this negative sign suggest? It suggests that m vector and L vector are oppositely directed. That is, the angle between the magnetic moment and the angular momentum is 180 degree. So this negative sign suggests that m vector and L vector are oppositely directed, as it's pretty evident from this particular diagram. So the negative sign suggests that m vector and L vector are oppositely directed. That is, the angle between m vector and L vector is 180 degree. Clear, students? Still, there is one more expression for the magnetic moment in terms of Planck's constant. So let's try to do that. So what we can do is, we can substitute the value of L as nh by 2 pi, which we obtained from Bohr's quantization condition in this particular statement, right? So let's find out the other expression for the magnetic moment in terms of the Planck's constant. Okay, what we do is, just now we have discussed, as per Bohr's quantization condition, the angular momentum associated with an electron revolving around the nucleus is given by some integral multiple of h by 2 pi. N is the principal quantum number. Right? This is as per Bohr's quantization condition. H, as I told you, it's Planck's constant. Right? So, what we do is, let's substitute this value of L over here. So, therefore, what we get is M is equal to E by 2M. Substitute this value of L as NH by 2 pi over here. So, what we get is NH divided by 4 pi. That is, M is equal to N EH divided by, actually it is 2 pi, right? NH by 2 pi. So it will be 4 pi M. Am I clear, students? What's the significance of writing this term in the bracket? It's because these terms are constant. E, electronic charge, H, Planck's constant, pi is constant, M, mass of the electron. So this term is constant. So M, it will have minimum value when N is equal to 1. And this minimum value of magnetic moment is known as Bohr Magneton. It may be termed as Bohr Magneton. So students, how do you define Bohr Magneton then? Bohr Magneton may be defined as the minimum magnetic moment, which is the magnetic moment associated with an electron orbiting in the first orbit of hydrogen atom. Clear? So it is basically the magnetic moment associated with revolving electron in the first orbit, of hydrogen atom. And obviously it will have minimum value, right? That is when n equals to 1. So Bohr Magneton is equal to, substitute the value of n as 1, so it will be EH divided by 4 pi m. You can substitute the values. E is 1.6 into 10 raised to the minus 19. Planck's constant is 6.6 into 10 raised to the minus 34. In SI obviously. Divided by 4. Pi can be taken as 3.14. Mass of an electron is 9.1 into 10 raised to the power minus 31 kg. You can easily solve it, and you should get about 9.3 into 10 raised to the power minus 24 ampere meter square. Ampere meter square is the SI unit of magnetic moment. So this is the minimum value of magnetic moment associated with the revolution of an electron in the first orbit of hydrogen atom. And this minimum magnetic moment is known as Bohr Magneton. So students, it basically gives an idea of the value of the magnetic moment associated with an orbiting electron. The order of magnitude of the magnetic moment is about, it can be considered to be 10. So 10 into 10 raised to minus 24. So order of the magnitude of the magnetic moment is about 10 raised to the power minus 23 ampere meter square. Got it, students? So this is it for this particular session. What we have discussed is an atom does behave as a magnetic dipole, and the magnetic moment associated is one of the expressions which we have found was EVR by 2. E is the electronic charge, V is the orbital velocity of the electron, R is the radius of the circular orbit. So this was one of the important expressions. Then we have discussed Bohr quantization condition. Then we have derived a relationship between the magnetic moment and the angular momentum, and then expressed the above result in the vector form. The negative sign suggests that the magnetic moment and the angular momentum both are opposite directed. And in the last step, we have discussed the expression for the magnetic moment in terms of Planck's constant. And there, by substituting the value of n as 1, we have obtained the minimum value of the magnetic moment, which is known as Bohr Magneton. Right? So students, that's it for this particular session. Do join me in my next lecture. We are going to discuss the types of magnetic materials in detail. That is, we are going to discuss about diamagnetic substance, paramagnetic substances and ferromagnetic substances. So till then, do take very good care of yourself, and thank you.